Hi, my name is Geneviève Bouchard. Welcome to Vehicle Dynamics series. For this first episode, we're gonna do an overview of the car to be more familiar about what we're working with. So today, Alexandru Bangala is here to present us the different subsystems. Hi, Alexandru. How are you doing?
Hi, I'm good, and you?
Good. So we're going to start by talking about the chassis, then aerodynamics and cooling, powertrain and drivetrain, dynamics, ergonomics, and we're going to finish by electronics and controls.
Yep, basically should be enough for you to have a good understanding by the end of the tutorial of the main aspects of the car. Not all in depth, but good enough.
So what do you know about chassis, Alexandru?
So the chassis is basically the foundation of a car where everything is connected to it. And our MFE 22 and future and previous cars, it is made of a carbon fiber monocoque, which is manufactured in-house, where we take basically carbon fiber sheets, we add epoxy, and we cure it to whatever thickness we want. We then added a front impact attenuator, which is mandated by FSAE, or governing body for the races and competitions, which has then been stress tested to meet personal McGill standards as well as legal standards. It has a quick release mechanism, which allows for quick replacement in case of a shock, and is also modeled to be as aerodynamic as possible. We've also included a top aerodynamic and cosmetic suspension cover, because as we get on later, the suspension or format of suspension takes up quite a bit of space, and to not sacrifice aerodynamicity, we've added this cover to also make it look nicer. In total, we aim about a 50-50 weight distribution front and back. The car also has a series of hoops, both around the driver's legs and on top of the driver's head, which help maintain rigidity in the case of either a crush or a rollover. It has now integrated harness straps, as you can see by the two arrows, so it also allows the seatbelt to be more comfortable. And the front hoop around the legs also stiffens the chassis, making it more maneuverable and prevents the driver's legs from being crushed. Around the chassis, we also have two main packagings. The rear packaging, which you see right now, contains the accumulator, which is basically the battery which makes your car move. It contains the inverter, the upside down board, which by itself just converts the electricity into a suitable format for the motors. We have the rear suspension and the main hoop braces, and we will get on to the first three later. In the front packaging, we now have also the front suspension. We'll get on that later also. The vehicle controller, which basically just tells the car what to do, when to do it, and analyze what the driver wants. We have the GPS, which allows us to estimate some of the driver's movements, a low voltage battery to operate them, as well as another pair of front inverters.
What does this front inverter do, like compared to the other inverter? Why do you have two of them?
They are identical, and in fact, we'll get into that later. But the car actually has four of them for each motor, and we'll get on that in the appropriate section. I just also wanted to add that MFE 22 and all MFE cars are manufactured to the highest level with in-house layups, high voltage welds, precision drilling, and all the CADs you have seen and you will see are used with professional tools like Siemens NX to ensure the highest chance of success and professional ability.
So now, can you talk a little bit more about aero and cooling?
Yep. So for aero and cooling, basically keeps us cool and on the ground. And in more detail, our car currently has around 400 newtons of downforce and about 115 newtons of drag. You don't really care about that number. What you care about is the distribution. Starting with the front wing, The front wing produces about half and a bit more of the downforce, and it only contributes to a third of the drag. It has been designed with a mid-span in the middle, which allows clean air to reach the under tray, which you will see later, which will reduce drag and provide passive cooling to the car. Going to the under tray, it adds about a quarter more of downforce and a tiny bit of drag, and it has been made with integrated side ducts, which you see on the top side, and strafes, the small leg horizontal boxes, if you can say, which help to direct the airflow where we want, in our case specifically to the radiators, and to take the disturbed air, which destabilizes the car and push it back. The rear wing, which is the biggest engineered aerodynamic component, apart from the shell, and our most recognizable element of MFE22, it adds even more downforce with one more quarter of it. However, because of the mass of the wing, it also produces half of our drag. Our vehicle is cooled with the help of two radiators, which you see here, along with two pumps running in series, which go directly to the motors, 4 of them, and to the inverters. Currently, they are continuously powered just by direct current. However, a controller has been built, has to be tested to allow for more automatic control and gain us a tiny bit more performance. All in all, it is very important to keep the inverters below 50 degrees Celsius and the motors below 120 degrees Celsius. Otherwise, we'll risk catching fire or just the car stops working.
So now can you talk about powertrain and drivetrain?
Of course. So the powertrain and drivetrain are what makes the car move. We're going to start with what provides the ability to move, which, because this is an electric vehicle, it is a battery, so the accumulator box I've showed you earlier. Inside of that box, which is surrounded by fans and sensors and everything, you have 288 lithium-ion cells, which are the most efficient and safest cells we could get, which are interconnected with a series of bars, which you can see a tiny bit over here, to provide a capacity of 6.4 kilowatt hours. So if we compare with a normal car, for example, my 2020 Fusion, which is hybrid, has about 7.6 kilowatt hour, a bit more, but the car also weighs more and uses more electricity. So this allows our vehicle to reach about 120, 130 kilometers an hour in a matter of 2.5, 3 seconds.
I just have a brief idea. Does the image at the right is in the image at left? Like, is it
exactly.
like in it? Yeah,
It is inside, and it is surrounded with fans and a box. The box is shock resistant, so the battery doesn't get crushed in an impact. And the fans are also around it to keep the battery from overheating.
Okay.
Moving on to the other part we saw in the main packaging, the inverter, in which are actually 4 inverters. Each one takes the electricity from the battery pack, which is direct current. It converts it to alternative current for the motors, and so the motors can actually spin. And the amazing thing about it is that it also allows for energy regeneration, which is basically once you're slowing down, it can do the opposite. So it takes electricity that is generated by the wheels and brings it back to the battery, which allows us for more range, more endurance, and less wear of the battery. Currently, because our car is all-wheel drive and has 4 motors, there's 2 of them in the back, one for the each rear motor, and in the front packaging that we saw, we have the other 2 inverters.
But where are those inverters? Like, there are 4. Are they like all like close to the wheels, or where are they on the car?
If we go back to the packaging, in the rear packaging, so where you see we have the rear hoop and where you have the rear wheels, it's the box which sits right under the suspension. And for the front one, it sits right below the driver's legs for the inverters.
So they are in pair of 2, like 2 in front, 2 at rear, but at the same place?
Exactly. They're all on the same common board, but
Okay.
the green section you see is actually one inverter and a second inverter. Now if we move on to what actually takes then the power. So we have German AMK in-hub motors, which means that inside the wheel hub where the actual tire and rim is attached, the motor is inside. It takes in from the inverter the input and converts it to about 84 Newton meters of torque. That doesn't sound like much, I agree. And then once it is mounted to the car to give it all-wheel drive, we have a one-speed gearbox, which is made in-house, which takes the 84 Newton meters and multiplies it by about 13 times more, 14 times more. So that measly 84 Newton meters we get converts to about 1100 and more Newton meters at the wheel. If we compare, for example, to a modern F1 car that most people know, a modern F1 car produces only about 670 Newton meters of torque. So we managed to make double what an F1 car does. It will not be faster than the F1 car because of the bigger power it produces by the battery and the hybrid motor, but it is still a very good contender off the line.
What is the actual function of the gear train?
So the gear train basically acts as both a gear train and a differential, in which it takes the spin that we see from the spindle here, which is about 84 Newton meters. And with the series of these three gears, a chain accelerates basically the output to the wheel that we see from the triangle right here. It makes the wheel spin faster than the actual motor provides. And because our ratio is 13.94 to 1, which is subject to change, it multiplies the actual torque from 84 to over 1100 that the actual wheel and the actual asphalt gets. So while the motor doesn't have to be strong, the result of just those three gears is phenomenal.
So the differential connects the motor to the wheels.
Exactly. We see here that the output of the gearbox is directly to the rim mounting of the actual tire.
So now can you talk about dynamics?
Yeah, of course. The dynamics is basically how the car handles and how we react to it. Starting with the most important part, the suspension. We have a innovative decoupled heave roll suspension, which are big words, in which the heave is basically the height of the vehicle. So as you're going around bumps, as you're going around different terrain, the car will go higher or lower depending on the surface. And what our suspension that allows us to do is to control the heave, the height, independently of the roll of the vehicle. So the roll is when you take a corner, you feel yourself pushed to the left or to the right. And we want to have different axes for it. We want the car, let's say, to move a bit more vertically than laterally. And this suspension allows us to fine-tune it exactly as we wish. Currently, that's it for the suspension. We'll get on to a lot more detail in the upcoming tutorial.
Yeah, exactly.
Now, moving on to our Brembo brakes. They have actually been derived from motorbike racing. So think of MotoGP or Moto2. And they're practically the exact same. Because of how smaller hubs are, they have also been chosen because of their optimal rotor heat transfer and their incredible efficiency compared to normal brakes to stop inside that tiny, small, little caliper surface area. The driver also has an adjustable brake bias, which I don't have a picture of the actual mechanism itself, but you do see on the right the hydraulics of the system, in which you can actually adjust when you're pressing the brake, how hard it actually presses the cylinders on it. And the reason we need these really small Brembo brakes is that a normal car has, let's say, a 16-inch, 18-inch, 19-inch rims or tires on it, so you have a lot of space for big brakes, which doesn't have to be as efficient. But we have 16-inch tires, but they're actually mounted on 7-inch rims. So that presented a really big challenge for us.
So is there one brake per wheel?
Absolutely, there's one per wheel, but there's actually only 2 cylinders. So the way it works is that one of these 2 tubes controls only the front, and the other one controls only the rear. And what the bias does when a driver modifies it is you can say, oh, I want out of 100%, I want 60% of the energy to go to the front, or 65% to the front. It's all defined relative to the front. And it just allows you to say drivers who have a heavier foot, who brakes more, has a tendency to lock up the brakes. And by moving the bias to the rear, so basically putting more force on the rear, it allows them to maintain better control than someone who is a lot more careful on the brakes. Moving on to the steering. It is very important to have predictable handling so as we don't end up spinning or we end up crashing when we don't want. So a comfortable geometry is essential. Our current column shaft is configured for what's called a double U-joint, which you can see on the third picture down here, in which it allows us to have really good reliability. And instead of a normal column where you just, when you turn the steering wheel, you turn a normal line, a normal rod, which is prone to braking if you move too fast, this universal joint can move about itself in every way possible. So all you have to do is just turn the steering wheel however you want, and it will never lock up, it will almost never break, and is one of the simplest but most reliable ways to use for a car. A fun fact is that while this is also pretty common in modern cars, it is also NASCAR racing approved and fairly inexpensive. So basically we're having safety, we're having reliability, and it's cheap to make.
Can you talk now more about ergonomics?
Yep. For ergonomics, it's how the driver feels, how the driver moves, what he has access to himself. Starting with the steering wheel. It is custom molded, so just apart from the main steering wheel made out of metal, we actually have the red grips you see here, which are molded for a specific driver with practicality and ease of access in mind for the buttons you see here. And what's interesting is that it's modular. So if I'm driving the car one day, I will have my own set of grips. If someone else is driving the car, he will have his own set of grips. And it just takes about 30 seconds to change, and you don't have to have any special tools for yourself. The steering wheel also has been recently changed from last year to allow more dash visibility by cutting out a piece in the middle of the steering wheel. You see on the right, the small piece of metal has been cut and replaced with plexiglass, just a piece of plastic, so nothing gets in the driver's helmet necessarily, and allows for more visibility to our dash or dashboard. And our dashboard is also modular and custom. So this is not a representation of our actual car. However, it shows what we can do for it. We can have it show us the torque, we can have it show us the speed, we can have it show us fuel or electricity usage, we can show everything that we deem necessary. And it also keeps a track of everything that happens in a car during a race. So after a race, we can go back, analyze, improve, or fix if something went wrong. The bucket seat is also seems like a simple, but it's actually really complicated design. It is fully made of carbon fiber. It is made in-house, and it has been designed to be as lightweight as possible while not being flexible, being rigid, and also allowing the driver to sit during hot periods in the middle of the summer and be comfortable while racing. Finally, going on to the pedals. The pedals are not like a normal car where you pull it and depending on how the cable moves, it determines how much to make the car move. They're actually hydraulically actuated, similar to F1. And as I shown you for the brake pedal, where you have two master cylinders, one for each to the front and the rear of the car. The accelerator is also similar in that the more you push the piston, that's the bright orange pistons, the more electricity is released for the car.
But what does hydraulically actuated means?
Yep, basically hydraulic, actually, there's a fluid, a non-compressible fluid. So think of water, for example, but a lot more robust. So the more you compress that fluid by pressing in the cylinder. Think as when you're like squashing potatoes, let's say. The more you press on it, the more pressure it generates because the fluid has to go somewhere.
Yeah.
And the fluid goes to the brake calipers. So what I showed you earlier, it goes to the brakes of the car to actually make the car stop. The accelerator, so the right pedal though, is made of a much compressible fluid. So it's easier to press because you don't want to have a lot of resistance when you're accelerating. So in comparison, the accelerator, you can press it like with your hand. It's enough to move it so you give it what you want. But the brake pedal needs a lot of force. You need to actually use all your muscles to press on it. But it allows the car to be very efficient and stop on a dime.
Okay. So can you talk about electronics and controls?
Of course. So in simple word, in just a simple sentence, electronics controls are what direct the car and tell it, if I do this, if I press this, then do that. If the car wants this, then what should I do? And all that has to be communicated in the entire vehicle with the use of a harness, which is a special word for a long sequence of cables that go around the vehicle a couple of times.
Yeah.
Basically, it seems as if it's just as simple as just putting the cables wherever you want and leaving them there. But actually the routing and the where you route the cables to is very important to follow the shape of the car. Because the last thing we want is for a wire to be cut or just to be pinched so nothing goes through. Because then we have to actually go through all these miles of wires and find what the problem is. And now I have to mention controls. So controls is what decides what the car does. And there's a couple of systems that we have integrated, starting with traction control and what's called as the maximum torque estimator, or the MT. Basically, traction control, TC, limits the slip of the tires. So slip is when you're accelerating and you hear the tire squeal, or you're not in control of the car. That is what slip is. And we have different modes in this system in which we can either just correct the slip by just cutting the throttle, cutting the acceleration, and then resuming once the tire regained traction. Or we also have what's called the MT, the torque estimator, in which we try to model the dynamics of the wheel. So we're trying to predict what the wheel should do versus what it does to actually limit the torque where it might cause this slip before it actually does, by using all the sensors from the harness I've mentioned before. Another very important system is the torque vectoring system, in which it makes sure that in corners, instead of preventing slip, it keeps the grip. So while slip is when a tire lost all grip, what we want here is to prevent that from happening even before the estimator kicks in. So because our car is all-wheel drive and has 4 different motors, the nice thing about it is we can actually tell which wheel gets how much power. So if we're going on a left-hand corner and we feel that we're going to slide off, we can cut the power from the inside wheel, the one inside the curb, and give more power to the outside wheel. So actually pushing the car in the turn. This one also has multiple modes. Either it does that continuously, which is better for endurance, but it's not the fastest way. It can only help during cornering, so when the steering wheel is actually turned. Or, of course, we can also turn it off for the purists who want to manage it themselves. So now the power cap is what I consider to be the most important control system of the car, because while a good driver will never use traction control and torque vectoring, no driver cannot use the power cap, because the FSAE, or association, limits the power at any time to 80 kilowatts. So if we're at 20 kilowatts, we're at the 80 limit. because it's calculated for each motor, and we have 4 of them, so we add up the 4 of them. And we will be disqualified, or we will have time penalties if we go above it. So this system basically continuously checks what the power draw is, and then reduces the power to a safe limit. So let's say 75, 76, 77 kilowatts to ensure we never get disqualified. And this system is very important because while it's easier to do when the car actually has grip and the tire has resistance, if we hit a bump and the tire suddenly doesn't have any resistance, the power to that wheel will increase a lot because the wheel will be spinning in the air. So it's very common in Formula Electric and Formula Student that once we hit a bump, the power draw goes to 100, 120 kilowatts. So this system hopefully prevents us from seeing those high numbers or those spikes. So basically, this is just a brief tutorial on how the car feels, how the car looks, how the car performs. It is not by any means anything that is in depth, but should be enough to get you started.
Yeah. Thank you very much. I would have a last question that may be a little tricky for you. You've talked about like all the different systems of the car.
Yes.
Where is vehicle dynamics like related to all of this?
Vehicle dynamics is, they don't really have a physical part in the car. Vehicle dynamics basically takes all the information from the sensors, or they do analysis using models and simulations, and then they help to actually tell us how to model the car. Should we focus more on suspension? Should we focus more on brakes? Should we focus more on power? By how much we should reduce the power? They're actually the ones who provide us with what aspect we should improve and by how much, and how we should engineer our car.
Yeah, vehicle dynamics is a lot about optimization.
Yes.
That's why in our next episode, we're going to talk about a lot about suspensions, ride dynamics, tires, and we're going to finish by talking about aerodynamics of the car. Okay, so thank you very much, Alexandru.
Thank you.
And see you guys in another episode.